Good morning, chemistry students. This is Mrs. Crumscheider, and we're going to go over ChemQuest 40 using moles with formulas. So we see information about percent composition here. Sometimes it is needful to know the composition of a compound. For example, 39.3% of the mass of sodium chloride is due to sodium. The other 60.7% of mass is from chlorine. So in a 100-gram sample of sodium chloride, there is 39.3 grams of sodium and 60.7 grams of chlorine. This type of data is known as percent composition. The percent composition tells you the percentage by mass of an element in a compound. There is a convenient formula for finding percent composition of an element in a compound. The percent composition of element X is the mass of X in 1 mole of a compound divided by the mass of 1 mole of the compound times 100. And these numbers both come from a periodic table. So with this, the clue and the key here is that they talked about having 100 grams because percent means per 100. So when you say that you have 100 grams of your compound, your percentages become masses. Okay, so that's going to be part of the key to kind of what they did there. So let us look at how the percent composition of calcium and calcium chloride was determined. So again, we see our equation, which I always want to see an equation written sort of like this one is. Okay, so the percent composition of calcium is the mass of calcium in 1 mole of calcium chloride divided by the mass of 1 mole of calcium chloride. Basically, right, this is the molar mass of calcium chloride that we just talked about the other day. Okay, I'm going to try turning off the light to see if that makes it a little bit better. Okay, so the percent composition of calcium, this comes from your periodic table for calcium. So that is the mass of calcium from the periodic table. Okay, and then this comes from adding up 1 calcium and 2 chlorines all together. Here's another example. Consider calculating the percent composition of nitrogen and calcium nitride. Again, they do it the same way. Okay, sorry about that. So, this first question, our critical thinking question. For the following questions, use 12.0 grams per mole for the molar mass of carbon and 1.01 grams per mole for the molar mass of hydrogen. These values can be found on the periodic table. So all they're kind of saying here is, okay, we're going to use 1.01 here and we're going to use 12.0 here. But those numbers are also on your periodic table. So it asks us to verify that in C4H10, the percent composition of carbon is approximately 82.6%. So if we want to do the percent composition of carbon, okay, it's the mass of carbon in 1 mole of C4H10 divided by the molar mass of C4H10 times 100. So that's our equation that I want to see. So next we're going to show plugging in our numbers. So our number here is going to be 4 times carbon because there are 4 carbons. Okay, so 4 times 12. Okay, so 48.0 grams. Okay, divided by the molar mass of carbon. So that's going to be 4 times 12 for the carbons plus 10 times the 1.01 for hydrogen. So we get 58.1 grams times 100. So we're going to do 48 divided by 58.1 times 100. And so we get 82.6%, which is what they said we should get. Now I like to put that it's carbon just to remind me that it was 82.6% carbon. So number 2 asks us to calculate the percent composition of sodium in sodium sulfide. So again, our percent, okay, composition of sodium equals the grams of sodium in 1 mole divided by the molar mass of sodium sulfide times 100. So there's my equation. So now again, I need to figure this out. So for sodium, when I look at my periodic table, sodium's over here, 22.990. Okay, so I'm going to use 22.99, and there are 2 of them, so I need to multiply that by 2. So I get 45.98 grams of sodium. Now, to figure out the molar mass of sodium chloride, I'm going to take the 22.99, multiply it by 2, and add to that the sulfur, which is 32.065. So that gives me 78.045. Times 100. So I'm going to do the 45.98 divided by the 78.045, multiply by 100. And again, in terms of significant figures, we could use 3 or 4 here. So we'll say it's 58.91%, okay, sodium. Okay, so that's what we got for our percentage of sodium. And that's the work that I want to see shown. So our next little section here is about formulas and percent composition. Table 1, percent composition and formulas for some compounds. So they give me the name, the structural formula, right, which shows us how all the atoms are connected to each other, the molecular formula, the percent composition of hydrogen, and the percent composition of carbon, which we know now how they would have calculated this. Okay? Number 3 says, verify that the percent composition of carbon and hydrogen given for hexene in table 1 are correct. Okay? So to figure out the percent of carbon, I'm going to do the grams of carbon in 1 mole divided by the molar mass of C6H12 times 100. So the grams of carbon in 1 mole, if we continue with our 12, and there are 6 of them, so that's 72, divided by the 72 plus the 12 times 1.01 for hydrogen, gives us 84.12 times 100. So I'm going to take my 72 divided by my answer, multiply by 100, and we'll go ahead and use, well, we could say this was 72.0, so we'll say 3 sig figs. So we get 85.6% carbon. Now, I have 2 choices for hydrogen. I can do this again, right? I can do the percent of hydrogen is the grams of hydrogen in 1 mole divided by the molar mass of the hexene times 100, okay? So again, I can do that again. I can do 12 times 1.01, which is 12.12, divided by the 84.12 grams. That's not going to have changed, right? My molar mass doesn't change. And so I can take that and divide that by the 84.12 and multiply it by 100 and see that I get 14.4. hydrogen. Okay, that's option 1. Option 2 relies on the fact that what do we know the two percentages have to add up to because there's only 2 elements? 100%. So option number 2 would be to take my 100% that it has to be the total and subtract the 85.6% that I figured out was carbon. And notice I also get 14.4% hydrogen. Now, my preference is this way. And the reason why is if you've made a calculation error in this answer, then this answer would be wrong as well. This way, if you do it this way as your second option, if these don't add up to 100, then you know that somewhere you've made a mistake. So again, I really don't care. I'm just going to tell you that, like I said, if you've done this incorrectly and you do option 2 this way, this answer is going to be wrong as well. So we just verified what number 3 asks us to do. Number 4 says fill in the blanks in table 1 by determining the percent composition and the molecular formulas of each compound. So let's do molecular formulas first, right? Where did the C6H12 come from? 1, 2, 3, 4, 5, 6 carbons, right? C6. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons. Okay, so here we have 1, 2, 3 carbons, so it's C3. And then we have H, and we have 2, 5, 6. So that's C3H6. Down here we have 1, 2, 3, 4 carbons and 4 hydrogens. Okay. And then down here I have 1, 2, 3, 4, 5, 6 carbons and 1, 2, 3, 4, 5, 6 hydrogens. Okay, so we filled in that part of the table. Now, you don't have to show all your math for this, right? So I'm kind of put my calculator here so you can kind of see, right? So for this one, we're going to do, for percent of hydrogen first, we're going to do 1.01 times 6. Should really should make it more clear that that's a subscript. Okay. Divided by 3 times 12 plus 6 times 1.01 times 100, and I get 14.4%. Now, right, 100 minus my answer, and I get 85.6% carbon. In my next one, again, hydrogen is first, so 6 times 1.01 divided by 6 times 12 plus 6 times 1.01 times 100, and I get 7.8%. And so 100 minus my answer, okay, and I have, we'll say 92.2%. Now, if this is 7.8%, this still has to be 92.2%, right? Because 100 minus 7.8 is still going to be 92.2. My last one, right? So hydrogen again, 6 times 1.01 divided by 6 times 12 plus 6 times 1.01 times 100. And I get 7.8% again, which means this has to be 92.2%. So we have filled in the blanks in table 1. Number 5 asks, can you determine a compound's structural formula if you are given the molecular formula, explain. So what it's saying is, okay, if all I see is molecular formula, do I know what the structural formula is? Now notice, we have a couple formulas there that are the same, right? C6H6 in the middle and C6H6 on the bottom. If that's all I have, do I know what the structural formula for that is? No. Okay, so for question 5, can you determine a compound structural formula if you are given the molecular formula? No, because we don't know which atoms are connected to one another. Right, in this middle one, it turns out that this is a cyclohexane, okay, a cyclobenzene, and in this bottom one, it's a straight chain, okay. The person who wrote this explained it, no. For example, hexene and benzene each have the same molecular formula, but different structural formulas, okay. And we see in the box, in table 1, we'll say, that there are compounds with the same molecular formula, but different structural formulas. Now, question 6. What is true about the percent composition of two different compounds that each have the same ratio of carbon to hydrogen? So, okay, what we're saying here is if we have the same ratio of carbon to hydrogen, right? This is a 1 to 2 ratio. This is a 1 to 2 ratio. This is a 1 to 1 ratio. This is a 1 to 1 ratio. And this is a 1 to 1 ratio. So what this problem is saying again is, what is true about the percent composition of two different compounds that each have the same ratio of carbon to hydrogen? So here we have two compounds with the same ratio of carbon to hydrogen, a 1 to 2. And what do we see about their percent compositions? They're exactly the same. These all have a 1 to 1 ratio, and notice our compositions are exactly the same. So what is true about the percent composition of two different compounds that each have the same ratio of carbon to hydrogen? The percent composition will be the same. Again, the person who wrote this explained it this way. If two compounds have the same molecular formula, they will have the same percent composition as well. So the same molecular formula means the same percent composition. All right, question number 7. Can you determine a molecule's molecular formula solely from the percent composition? So again, what this is saying in this question is, okay, if all I can see is the percent composition, do I know what the molecular formula for this compound is? No, right? I don't know what the molecular formula is. For this top compound, it's C6H12. In this one, it's C3H6. With these, we have C6H6 and C4H4. So the answer to that question, can you determine a molecule's molecular formula solely from the percent composition? No, okay, because it's really just giving us the lowest whole number ratio. Of atoms in the compound. Again, the person who wrote this explained it no. As can be seen in Table 1, compounds with different molecular formulas may still have the same percent composition. Okay, so we can have the same percent composition, but different molecular formulas. Number 8, is it possible to complete the following table using only the information in Table 1 without the aid of a calculator or periodic table? Try it. Hit consider question number 6. So this is saying can I use this table to complete this? So notice my molecular formula is C8H8, right? This is a ratio of 1 to 1. And what do we know about all the 1-to-1 ratios? The percent composition of hydrogen was always 7.8%, and carbon was 92.2%. This ratio is a 1 to 2. What do we know about our 1 to 2s? Well, they're 14.4% hydrogen and 85.6% carbon. So the answer to that question is yes, we can. Okay. So again, what we want to notice is that any compound of carbon and hydrogen with a 1-to-1 ratio, not ration, ratio, has the same percent composition. And, okay, any compound of carbon and hydrogen with a 1 to 2 ratio has the same percent composition. Okay? An empirical formula is a formula that describes the lowest whole number ratio of elements in a compound. An example of an empirical formula is CH, which is the empirical formula for benzene, whose molecular formula was given in Table 1. So benzene, right, in Table 1 was C6H6. Okay, so that was our molecular formula. They're telling me my empirical formula is CH. And it's the lowest whole number ratio, right? 6 to 6 is the same as a 1-to-1 ratio. What is the empirical formula of a compound whose percent composition is 92.2% carbon and 7.8% hydrogen? See question 8 in Table 1, right? So if I have 92.2% carbon and 7.8% hydrogen, then I have a formula that has a 1-to-1 ratio. Okay, so it would just be CH. Okay. And again, that's because any compound with a 1-to-1 ratio has those percentages. Verify that the empirical formula for hexane is CH2. See Table 1. Okay, so hexene, which is this top one, C6H12. That's our molecular formula. So our lowest whole number ratio would be CH2. So it is, because that's our lowest whole number ratio. Calculating empirical formulas. So this kind of goes through one way to do it. We're going to do it a little bit differently. Okay. It doesn't matter really much to me so long as you show your work which way you do it. So number 11 asks you to find the empirical formula of a compound that contains 82.4% nitrogen and 17.6% hydrogen. I'm going to say this step number 1. Okay. Step number 1, okay, is that we are going to assume we have 100 grams of our compound. Therefore, our percentages become grams. So we're going to have 82.4 grams of nitrogen, and we're going to have 17.6 grams of hydrogen. Now, part of our goal here is one of the ways that we can interpret a formula like NO2 is that this is 1 mole of nitrogen and 2 moles of oxygen. So we want to convert our mass to moles. And remember, we have a tool that allows us to do that on our toolkit. It's called molar mass. And again, we're going to kind of do both of these at the same time. Okay. Now, remember, where do we get our numbers for molar mass? From our periodic table. So our periodic table for nitrogen, and we want to use 3 significant figures. So our mass for nitrogen is 14.007. So we're going to go ahead and use 14.0. For hydrogen, we're going to use the 1.01. Okay, so I'm ready to kind of do a little calculating here, right? So 82.4 divided by 14. And we're going to use 3 sig figs, so we're going to say it's 5.89 moles of nitrogen. And 17.6 divided by 1.01, we have 17.4 moles of hydrogen. Now, the problem is I can't write a formula with N 5.89 and H 17.4. I need them to be whole numbers. And so, okay, our step number 2 was we're going to use molar mass to convert grams to moles. Step number 3, okay, we want whole numbers. So our trick is going to be we're going to divide all the numbers by the lowest number. And our lowest number is the 5.89. So when I take this number and divide it by 5.89, I'm going to get 1. When I take this number and divide it by 5.89, I get, okay, 2.96 moles of hydrogen. Now, this is really, really close to 3, right? So we're going to kind of round this to 3. So what that means is our empirical formula is N1H3, right? And so we would just write it NH3. So that's a little bit different set of steps than what the person who wrote this ChemQuest did, but they ended up with the same answer. And when we take notes in class, this is how we're going to do it. So we got this by dividing it by 5.89. All right, calculating the molecular formula from the empirical formula. Remember that the empirical formula is just a simplification of the molecular formula. For example, Consider the empirical formula NO. There are several possible molecular formulas, including N2O2, N3O3, N4O4, etc. Which one is it? Notice that the possible formula N2O2 is made up of two of the empirical formulas NO. Similarly, N3O3 is made up of three of the empirical formulas NO. How do we know which empirical formula is correct? All you need is the molar mass or molecular mass of the molecular compound. So number 12. Okay. And what this was saying here is when I have NO, if I take this and multiply it by 2, I get N2O2. If I have NO as my empirical formula and I multiply it by 4, then I get N4O4. Okay, that's what that was saying. So number 12 says, the empirical formula for a certain compound is NO, so this is my EF. The molar mass of the compound is 60 grams per mole. This is the mass of my molecular formula. Okay? So what is the molar mass of the empirical formula? Use the periodic table. So they want me to figure out the mass of this. Okay? So I'm trying to figure out the mass of, okay? I want to figure out, letter A is asking me to find the mass of NO. So that's just like we've done before, right? So that's 14.0 plus for nitrogen plus 16.0 for oxygen. So the molar mass of NO is 30.0 grams per mole. And we got that from adding 1 nitrogen plus 1 oxygen, okay, together. Now, okay, I like that. Now it says we want to figure out what this ratio is, like we did here, right? If I had N2O2, okay, I want to find this ratio. So to find that ratio, I'm going to take the mass of my molecular formula and divide it by my empirical formula mass. So I call this the EFM, and I call this the MFM. Okay, so this is my MFM. So my molecular formula mass was 60. I have calculated my empirical formula mass to be 30, which is 2. So what that means is I'm going to take my empirical formula and multiply it by 2 to get my molecular formula. So my empirical formula was NO. I'm going to multiply it by 2, so I get N2O2. So this is my molecular formula. So it tells you, your answer to part B tells you how many empirical formulas are in the molecular formula. Basically, it's telling us how many times we have to multiply by. You should be able to write the correct molecular formula, which is N2O2. Okay, so we just did that. So question 13. What is the empirical formula of a compound whose percent composition is 85.7% carbon and 14.3% hydrogen? So this is asking us, right, to do all of those steps that we did, right, that we did up here. Okay. So step number 1, assume we have 100 grams so that our percentages become masses. So that's what I did. Step 2, use molar mass to convert grams to moles. So 12.0 grams of carbon for 1 mole of carbon and 1.01 grams of hydrogen for 1 mole of hydrogen. Remember, the 12 and the 1 come from my periodic table. So now I do a little calculating with my calculator. 85.7 divided by 12, I get, okay, 7.14. So 85.7 divided by 12 is 7.14 moles of carbon. Now, here's a little trick. You can store your answers on here. Let me remember how to do that right here. So I want to store this answer so that I don't have to type it in again. And I'm going to store it as A. And what I sometimes do is I kind of make a little note to myself to remember I've stored it as A on my paper. Now, I want to take 14.3 and divide it by 1.01. So I get 14.2 moles of hydrogen. And again, I'm going to go ahead and store that as B. Okay, so that's my B. So remember, I need whole numbers at this point, and I don't have whole numbers. So I'm going to divide them both by the smallest, which is the 7.14. This is going to be 1. Okay, and so I'm going to take this answer, and I'm going to divide it by I'm going to say second recall, and I want A. And I get 1.98 moles of hydrogen, which is about 2 moles of hydrogen. So my empirical formula is CH2. Now, part B, right? Because that's what it asks us to do, the empirical formula. Part B, if the compound has a molar mass of this, what is its molecular formula? So I need to find the mass of my empirical formula, which is just going to be 12 plus 2 times 1.01, 14.02. They told me my molecular formula mass. They said it was 56 grams per mole in my problem. So I want to find my multiple. So I'm going to do my molecular formula mass divided by my empirical formula mass. My molecular formula of mass is 56. I'm going to divide it by my 14.02 and figure out what my ratio is. So I'm going to do 56 divided by my answer, and I get 3.99, which we would call 4. So that means I'm going to take CH2 and multiply it by 4 to get my molecular formula. So my molecular formula is C4H8. So I hope that helps you out if you were struggling a little bit with this ChemQuest. Have a great day, and I will talk to you tomorrow.